Hello and welcome back. In this video we're working through an important derivation, the goal of which is to describe the motion of an object in a gravitational field. So we'll be just starting with two-dimensional motion in this video. In a later video we'll work on three-dimensional motion. So just two-dimension here, and we'll be starting with just Newton's second law. And so we're going to derive the position function, velocity function, acceleration function just from first principles, just from Newton's second law. Right, so Newton's second law tells us that mass times acceleration equals force, right? F equals ma. Of course, what this really means is that the sum of the forces acting on an object, and we're thinking of these here as vectors, right? Sum of the force vectors acting on an object is equal to mass, a scalar, right? So keep in mind mass is a scalar here, multiplied by the acceleration vector, right? So here we have a vector, A of t. Right, so you add up all the forces acting on an object, divide that by the mass, and you get the acceleration. That's one way to think about this. Right, so again, we're just starting with two dimensions here, and our other assumption, right, another big assumption here is that we're just going to be thinking of the only force acting on the object is gravity. That's the idea. So the idea is we're essentially going to launch some object. We're going to shoot it with some initial velocity, some initial position off into the blue, and let gravity act on it. And then we want to describe that motion, right? So again, find position, velocity, and acceleration. So with this F equal ma, Newton's second law, this tells us how to get a hold of acceleration, right? It relates it to the forces acting on it, and the forces acting on it we know. So F here, our forces acting on the object, will be 0 and then minus mg, right? So mass, again, this is mass of the object, multiplied by acceleration due to gravity. Acceleration due to gravity. Now this could be in or meters per second. This could be in meters per second squared or feet per second squared. Remember that if we're doing meters per second squared, g is 9.8 meters per second squared, or this is sort of the typical approximation we use, or we use 32 feet per second squared. Right, so this is our g. Right, so that tells us mass times our acceleration vector is equal to this vector 0 minus mg. Right, why does my vector look like this? Well, because force acts in the downward direction, and so that is why we're seeing minus mg in the y component of this vector, right? So the y component is describing the up and down motion of the object, whereas the first one is the left to right, or lateral motion of the object. Okay, so what else do we have here? So that means, right, if we know m times the acceleration is 0 minus mg, divide both sides by m, we get, yeah, of course, the acceleration on the acceleration of the object is 0 minus g. This makes sense because gravity is the only force acting on the object. Again, it's minus g in the y component, so that's an acceleration of g downward. And then, right, so we do have initial conditions here at t equals 0. We're going to keep these general. I want to develop a formula that's going to work no matter what we're given as an initial velocity and initial position. So for initial velocity, I'll use u0, v0, and initial position, I'll use x0, y0, or x0, y0. All right, so let's derive now the velocity and position function. So here's our acceleration function. It's constant. That's important. We have constant acceleration. And let's go ahead and get a hold of velocity. Will be our next one because keeping in mind, right, that the antiderivative or n antiderivative of acceleration is the velocity function, right? So I want to find n antiderivative. Gives me this. All right. So we'll start there. So v of t is indefinite integral of a of t dt. Right, and we are integrating vectors here, but we talked about that earlier on. in this chapter, and so we can do that just fine. We get velocity out. A of g, so this is integral of 0 minus g dt. That's not too hard to get, right? Integrate in both. I will get, let's say, c1, so some constant, right? I get an this is an indefinite integral, so I get constants out, and then I'll have what, minus gt plus some constant in the y direction. So how do I figure out these two constants? Well, I use my initial condition, v of 0 is, so on one hand, it's c1, c2, right? Because if I plug 0 in for t there, that goes away. I would just have c1, c2. On the other hand, it's also what I'm calling u0, v0. So really, this u0, v0, u0 is c1, v0 is c2. That's my initial velocity. That's what these constants are that come out of the indefinite integral. So this tells us then v of t is, so this vector function is the initial velocity in the horizontal direction, right, in the x component. That makes sense that it should just be this. It should be constant in the x direction because there's no forces acting on it in the x direction, just in the y direction. So in the y direction, we should see, yeah, minus gt plus my v0. Right, so if I have an initial upward velocity, this v0 will be positive, and then gravity will be working against it. Right, notice the negative on the gt. Cool, so that's velocity. To get position, we simply find an indefinite integral of velocity. v of t dt. So what'll that look like? That'll look like u0 t plus some constant. Let's call this one k1. And then over here, I'll have minus 1/2 gt squared. Almost forgot how to integrate there for a second. Minus 1/2 gt squared plus v0 t plus some constant in the y direction. Of course, these constants, right, if I plug 0 in for t, these are the only constants that remain, right? R of 0 is k1, k2, and that is my initial position, right, which is what I'm calling x0 and y0. So what we have here is that R of t is u0 t plus x0 and minus 1/2 gt squared plus v0 t plus y0. Right, so our y component here should look very familiar. You've probably used this formula before for motion in a gravitational field. Specifically back in Calculus 1, we recovered this. We went through this derivation, but it was just for the y component because we were just looking at a function, height, in terms of time. Right, that's typically the setting that we investigate gravitational fields in Calc 1, right? Height versus time. So that's my y component versus time. That's where this comes from. But of course, at the same time, right, our x position, our lateral position of our object is also changing, and that's described by this linear function of time here. And again, it should make sense that this is linear because we just have an initial velocity of u0, and there's no forces acting on it. So it's just linearly increasing. Great. So these are important equations that we get out of this. Vector equation for position, vector equation for velocity. In the next video, we're going to use these things to describe particular motion. So for instance, this is what we'll work through. A baseball being hit from 3 feet above home plate with this initial velocity. The things we're going to work out, what we can now do with this vector equation, right? We want to do some extra stuff with this now that we have vectors. Things we can figure out and have nice formulas for are things like range, max height, and time in flight. So we're going to work out what these quantities are in terms of these initial positions and things like that. So that's the next step. That'll happen in the next video. Can't wait. I'll see you there.